是做钠钾离子电池的很有名的一个教授。因为这个签证的原因啊，没有能到现场。我们下面播放他的一个讲演。开始。
I would like to present my recent contribution and progress on sodium ion and potassium ion chemistry, in particular, development of new hard carbon sharing 480 mAh as beyond lithium graphite interconnection compound. So, first, it is very unfortunate that I cannot travel and meet Chinese friend and also worldwide friend in person this conference because of visa issue. I cannot travel and come to China this time, but I would be happy to have opportunity to introduce my recent contribution online. So first, I would express special thanks to the organizers, in particular Dr. Liu, to give me opportunity to deliver inviting talk. When I was a PhD student, I spent some years with Dr. Liu, who is very kind and also motivated me to study battery materials as well as electrochemical devices. And Professor Osaka on the right picture, who he encouraged and also lead us for motivating me to develop new batteries and also new analysis to understand battery reactions. So first, I'm now belonging to Tokyo University of Science. My university is highly related to battery technology, especially manganese dry cell. It was first developed by Mr. Yai, who studied my university over 100 years ago. Actually, after establishment of my university, and one guy, Mr. Sakizo Yai, was highly interested in to develop battery powering for clock, watch. In order to make convenient watch clock, he decided to develop dry cell without liquid, and he succeeded in development first commercial dry cell in 1887, more than 100 years ago. This was developed based on improvement of manganese wet cell, which was first developed by French engineer. And in a modern dry manganese cell is working with potassium hydroxide aqueous solution. Please note that it is potassium. So this story was recently introduced in Nature in an advertisement feature in last year. In this article, not only me but also real Yai's battery and the state-of-art rechargeable battery, sodium and potassium-based ion battery are introduced in this article. And please note that the real one is now exhibited at my university. So in a recent alkaline cell like manganese cell and also nickel metal hydride cell is filled with 6 molar potassium hydroxide aqueous solution, which is showing highest ion conductivity for aqueous battery cell. So why potassium? Because potassium shows less and smaller size than lithium and sodium hydrolyzed condition. And also after dissolving lithium, sodium, and potassium salts, achieved by using potassium counterpart because of smaller hydrolyzed ion size. So potassium or sodium are essentially advantageous than lithium in terms of ion conduction and also higher transportation number in liquid electrolyte solution. Actually, by comparing the hydrolyzed side and also crystalline ionic side, potassium showing larger ionic side, but potassium shows smallest Stokes radius in water or organic electrolyte solution, so that potassium and sodium shows higher conductivity, higher transport number, and also lower viscosity than lithium electrolyte solution. These features are advantageous, remarkably advantageous for high power battery than lithium ion. So this is the outline of my talk, and first, I will emphasize that the motivation towards sodium and potassium batteries of lithium ion battery. So when I was a student, we learned that lithium is best choice, theoretically best choice for lightweight and high power, high energy density battery because lowest E0 and also lowest atomic weight among any metal elements. Based on this feature of lithium character, lithium cobalt oxide and graphite combination works well as lithium-ion battery over the world and over 30 years. By charging this battery, lithium can move from positive to negative electrons. Then lithium intercalcium compound like lithium GIC is formed on the negative side of the copper current collector. However, in recent years, we need more and more rechargeable batteries, but the issue is costly metals like cobalt, copper, and lithium are necessary for lithium-ion battery. In order to tackle this issue, one of our personal opinion is the best choice should be potassium and sodium-ion batteries, because these new batteries are free from costly metals like copper, lithium, and cobalt. So when we look at the history of sodium-ion battery, the earlier success of sodium-ion battery than lithium commercialization by Sony was found about 3 years earlier than lithium. This sodium-ion patent was applied by Showa Denko, Hitachi, and Allied Signal, 3 company collaboration. And in this patent, the positive and negative electrons are based on cobalt and polypropylene green conducting polymers. 3 years later, the great rush of the lithium-ion battery, which was commercialized by Sony, Japanese company. And after about 20 years, we reported the first sodium-ion battery based on combination of hard carbon and nickel manganese radiant oxide. And in recent years, Chinese company CATL is released that sodium-ion battery is commercially and practically used in 2023. And also, many of researchers over the world is now focusing on solid lithium-ion battery, lithium sulfur, lithium air, magnesium, calcium, and aluminum batteries. So, in 2009, we succeeded that demonstration of sodium-ion battery based on hard carbon and nickel manganese radiant oxide, and this shows average volts of 3 volts and acceptable charge discharge cycle life by developing new electrolyte solution for sodium-ion battery. Our earlier success in 29, then we have great rush of sodium-ion battery development. And as you can see here, the number of scientific papers drastically increased after 2010. And last year, or 2 years ago, we have more than 3,000 papers per year which have been published over the world. Based on this background, CATL is released that sodium-ion practical use of sodium-ion battery. Because of larger number of publications, we also had opportunity to submit review paper on research development of sodium-ion battery, which was invited by Professor Whittinger, who is Nobel Prize laureate in 2019. And also about 3 years ago, we also published research development on potassium-ion batteries. Lithium needs costly and minor metals like lithium, cobalt, and copper. On the other hand, nickel metal hydride, nickel cadmium, and lead acid also needed not only costly but also toxic and corrosive chemicals inside the battery. On the other hand, in case of sodium and potassium batteries, which are toxic-free and lower cost compared to lithium-ion, which are quite advantageous for future sustainable power sources and as next generation batteries. And of course, our target is higher energy density, higher performance than conventional lithium-ion, and also by using sodium and potassium integration electric materials. So based on our motivation, today I would mention about sodium and potassium ion electrode and also electrolyte materials. And first, I mentioned about hard carbon negative electrode as beyond lithium GIC. So about our first demonstration in 29, the reversible capacity for hard carbon was 260 mAh. This time, hard carbon was kindly supplied by Cleha Corporation. But after that, we had effort to develop higher capacity electrode materials. And finally, 2 years ago, we printed 480 mAh, which should show higher energy density than lithium GIC. So because of our successful development of long cycle life hard carbon, then we are able to analyze the sodium insertion mechanism based on highly reversible electrolyte system. And our collaboration with Professor Goto and Dr. Oishi, we understood that sodium integration into the interstitial layer spaces, then at lower potential region, sodium cluster formation in nanosized cores. Then we can demonstrate 250 mAh. Based on this understanding, we tried to prepare high-capacity hard carbon by using different starting material and also different synthetic routes. And our latest success was magnesium oxide templated carbon. This carbon was this synthetic route was developed based upon the control of pore structure in magnesium oxide templated nanoporous carbon, which was published over over 10 years. So based on these nice works, we successfully developed a new temperature synthesis of high-capacity hydrocarbon sodium-ion battery. So how to synthesize based on temperature material? The key point is how to mix raw materials. The conventional technique was powder mixing of magnesium gluconate and glucose, which are the starting materials for hydrocarbon. And our new synthetic route is like that, based on freeze drying. For freeze drying, first we dissolve this magnesium gluconate and glucose dissolving in water. Then to maintain atomically homogeneous mixture, we treated it by freeze drying process. Then we have very homogeneously mixed precursor. Then we carried out calcination, that is carbonization based on these starting materials. Then we have highly dispersed magnesium oxide template in carbon matrix. And after post-heat treatment of this precursor, we have very high capacity hydrocarbon for sodium-ion battery. So synthetic route is like that. The glucose and gluconate magnesium oxide fluid was homogeneously mixed through freeze-drying process, and then we have porous nano-sized pores inside the carbon matrix. Then finally, post-heat treatment at 1,500 degrees C, we successfully prepared high-capacity new hydrocarbon. So as you can see here, TM observation confirms that we have carbon matrix and incorporating nano-sized 1 or 2 nanometer diameter white dots dispersed in carbon matrix, which are corresponding to magnesium oxide crystals, and which are smaller than this one. These are through synthesized through powder mixing, mechanical mixing of two starting materials. So freeze drying homogeneous, atomically homogeneous mixture is very important to make a smaller size of template magnesium oxide. And finally, based on such small particle template synthetic strategy, we demonstrated 480 milliampere hours capacity corresponding to sodium C4.7, which are higher concentration of sodium than lithium in lithium GIC, lithium carbon 6. Details synthetic route are reported in this recent publication. So to compare the energy density, we assume that 4 volt lithium positive electron, which is corresponding to 3.7 volt in sodium cell. So in case of lithium GIC, we can achieve energy density of this area corresponding to 1,420 watt-hours per kilogram. But by replacing sodium hydrocarbon showing high capacity, and by assuming the same positive electron potential limit and capacity, then we achieve that almost 20% energy density gain than lithium GIC cell. This means that the area surrounding the positive and negative potential variation, this red area is 20% wider than blue area of lithium ion cell energy density, which is highly advantageous to demonstrate the high performance sodium ion battery than lithium. So not only negative electron, but also we are recently focusing on negative electron. First, our trial was based on nickel manganese, and recently much more abundant positive electron material based on iron, manganese, and magnesium. So P2 type layered sodium iron manganese oxides are shown here. And the redox reaction based on manganese and iron free for positive redox couple, we can demonstrate that 180 million hours. So by doping with copper or magnesium, and also we have larger amount of sodium, then we have higher capacity and also matching higher fast charging capacity, which are advantageous to design AC ratio of sodium ion cell. So next, I will introduce our potassium ion battery, which is brand new battery based on graphite and potassium blue, negative and positive electrons respectively. So what is meant for potassium ion, which is heavier atomic weight than lithium and sodium? In case of lithium and sodium, the potential wind is narrower for sodium ion because sodium operating potential is higher than lithium. But it is surprising that in case of potassium operating potential is lower than lithium because the operating electrochemistry medium is based on propylene carbonate or EC or DEC like carbonate ester solutions. They are not water aqueous solutions. So potassium operating potential is lower than lithium in propylene carbonate electrolyte solution. Then wider potential window than lithium and sodium, which means that it is highly advantageous for higher voltage operation, which will lead to higher energy density by using same capacity electric material for positive and negative electrons in lithium and potassium cells. Actually, based on manganese iron hexacyanoferrite complex compound for positive and graphite negative electrons, and also we can use aluminum current collector, we should demonstrate higher energy or comparable energy density for potassium ion cells to lithium cobalt and manganese pair lithium ion battery. And please note that in case of potassium cell, which is based on potassium ion aluminum manganese and which is free from lithium cobalt and copper, which are costly metals. Because of our success of potassium ion cell for forward potassium GIC and full cell based on iron manganese positive electrode, the number of publications drastically increased. And our first report on potassium integration into graphite was published 8 years ago, and KC8 is highest concentration of potassium in graphite, which is lower than lithium, but comparable capacity, reversible capacity to lithium cases. And charge covered here. And also we have to select good binder like polyacrylate and good electrolyte solution. And we also reported the precise electrochemical precise analysis of potassium integration process based on operando electrolytic reactions. And key issue is electrolyte for potassium ion cell. We have some publications for new electrolytes for potassium ion based on our earliest finding for negative and positive electrons. And in recent years, we also reported SL forming additives and also state potassium ion cells. So let me introduce first one is electrolyte for SL formation. So as chemical analog of FSA anion, we have two methyl group and DMSF additive version successfully found for quite efficient electrolytic additive for potassium ion battery. And by adding DMSF, capacity retention are highly highly improved rare earth higher coulombic efficiency over 100 cycles, 500 cycles. Also, we reported recently the all-solid-state potassium ion polymer batteries based on polyethylene oxide potassium ion conducting polymers, which shows one-position window to match with graphite and iron hexacyane ferrite positive electron cell. So let me conclude myself. Lithium, sodium, and potassium ion chemistry. This systematic study will be leading us toward next generation battery technology. I mean that based on sodium and potassium understanding, we can design new interpolation electron material and new lithium ion conducting electrolyte for advanced lithium-ion battery. So based on these systematic studies, we should challenge sustainable energy storage devices for carbon neutral society. So this is the photo of our research team. So thank you very much for your kind attention.